question. We can discuss. I want to hear your thoughts.
Sorry.
So we'll start now then. This is a question that some of you probably thought about before. Why do computers only use zeros and ones? Like, why don't you ever see computers using 2s or 3s or 42s or anything like that? They're all always talking about the binary when it comes to computers. Why do you think that is?
It's because most physical systems, I mean, classical bits are have 2 levels that you use.
That's probably a big part of it. Yeah, I think transistors are, they make up most computers, and I think those are more conveniently described by zeros and ones. But it makes you think, though, why, if it's just the transistors, like what if we built computers out of something else? Then couldn't we do computing with more than just zeros and ones? You know, what's stopping us? So actually, this has been done before. Non-binary, I don't think that's the right word. I used it. More than just zeros and ones, that is, have been used in the past. This was a cool thing I found when researching this. This is in 1958, this computer in Moscow was built using negative ones along with zeros and ones. I don't exactly know how they did that, but they had to develop it in its own unique way, which is different from the binary computers that ended up overtaking it. But it had some unique advantages back when it was around, and that is doing math with negative ones along with zeros and ones is sometimes just more convenient than doing math with zeros and ones. And apparently Donald Knuth described this ternary system as perhaps the prettiest number system. It's so balanced. Got 1 on the one side, -1 on the other side. So one interesting advantage is that it doesn't take, you don't need to add an extra bits to an integer to make it signed. You can just use the negative ones that are included. So you get positive and negative integers built in. So this is one example of thinking outside the box with binary. You know, you can think of, there are some obvious drawbacks to using just zeros and ones in computing. Like, say, for example, your problem requires you to have a number that's between 1 and 200, but it's never going to be more than 200. But if you want to store that number as in your binary system, you need to make it an 8-bit digit, which goes all the way up to 256, even if you're not using all of that extra space. So in a sense, it's kind of wasteful to always stick to zeros and ones. Of course, that doesn't matter nowadays because we have so many bits, we don't know what to do with them. But it's still worth keeping in mind. Yeah.
Would you mind sharing your screen on the Zoom? I just realized
you're
presenting here, but on Zoom.
Zoom doesn't see me, huh? Okay.
So I think if you go to, yeah, perfect.
You said we were all ready.
Yes, you can share your screen, the green button. Yeah.
Okay. Here's my screen. Slideshow mode. Okay. All right, we're back in now. Is it working?
Yeah. It is. Yeah.
Okay. Yeah. So that was an interesting thing I thought I'd start with. Another thing that we ought to think about, since we're dealing with quantum computers, is analog computing. So this is something that I'd say often gets confused with quantum computing. Say you're describing quantum computing to someone who's never heard of it before. You might say, well, classical computer uses zeros and ones, but quantum computer has superpositions of zeros and ones, so it can be anywhere in between. And then they'll usually say, oh, wow, yeah, I see how that can be better, because then you have so much more space to do computing. But actually, what that's describing is already possible without quantum computers. You could just have an analog computer, say, imagine using sliders or mechanical pieces to do computations on numbers that are not just 0 or 1. So the question is, how is this different from quantum computers? Does anybody have an idea, an answer? What's the difference that sets apart quantum computers, which are in superpositions of 0 and 1, from analog computers, which are just any real number between 0 and 1?
Computer, you can actually measure 0.5 like any of the spectrum of values.
Okay. Well, then doesn't that make analog computing better?
You didn't ask me to promote.
Yeah.
Would you get extra degree of freedom on the computer?
Extra degree of freedom?
You have like a
Yeah.
theta and phi, right? So you have two, as an experiment, 2 knobs to turn. And in an analog computer, you have 1 knob to turn, which is the value of the voltage, for example. With more tools.
Sure, but you could just use twice as many analog bits, and then would that still be the same?
Right. Then you're using twice as many bits.
Mm-hmm. Well,
I think it's fundamentally.
there's something more fundamentally different. And what I'm trying to get at is the big difference that sets quantum computing apart is entanglement. There's no classical analog to quantum entanglement because it's a purely quantum effect. You can't observe it on any scale that you would do this analog computing on. So that's another important thing to keep in mind, the importance of entanglement when it comes to quantum computing. And that's a sort of a segue into qubits. We all know and love the qubits. You can see on the block sphere, it is a sphere, so it does have an extra degree of freedom, of course. But I want to sort of think about these in the same way we just thought about classical bits, 0s and 1s. Why do we use 0s and 1s in computers? Well, why do we use qubits in quantum computers? There are a few reasons that I'll talk about. So there's the obvious reason that it's a direct analogy to the 0s and 1s that everyone's used to. And so that makes people happy. It's also one of the simplest systems which are capable of exhibiting quantum effects. So superposition and entanglement, those are the big ones. And you need those to be able to do effective quantum computing. There's also lots of different ways that you can implement them. So being able to have real quantum computers is important now. Like, for example, the spin of one particle can be up or down. That's a qubit. There's 2 possible states, and it can be in a superposition. Another is a photon can be polarized horizontally or vertically, or in any superposition of those 2. So that's another example of qubit in nature. And when we build quantum computers out of these qubits, you need to be able to do a few things. Right. So here's more examples of actual quantum computers using qubits. You need to be able to do a few things. You need to have the 2 quantum states in this system. You need to be able to measure them. Otherwise, you're just doing computations and not knowing what the results are. And you need to have some sort of way to manipulate them. So have like some sort of logic gates that you can apply to your system. So here are some neat little diagrams of quantum computing systems that are out there right now. There's the superconducting circuits, which are used by IBM and others. There are quantum dots. That's where you have an electron trapped in a silicon ball and you manipulate its spin with microwaves. There's also trapped ions, where the 2 possible states are an electron being in 2 different energy levels in the ion, and that can be manipulated with light. Then there's also topological qubits, which is a bit more abstract, And Microsoft is working on these, but I don't think they have any physical system yet. But it's something very weird with braids and geometry and topology. But I thought I'd mention that too, because it was in the same diagram. But another thing to note that I wrote again here is that in order to actually use these in a quantum computer, so you want to build a computer out of lots of these and connect them, you need to also be able to exhibit entanglement between two pieces of the system. So I'm going to talk a little more about the superconducting qubits. That's what IBM uses. Apparently, they're the forerunners now with 400 qubits on their new system. Those are made up of these special circuits which use the critical components, the Josephson junction, which is represented by that the blue X's on the far right of that circuit diagram. Those, I think Joe talked about those in his talk. If you want to learn more about these, I'll just gloss over them. But essentially they use Cooper pairs, which are how electrons move in superconductors, to create quantized energy spectrum in the Josephson junction, which is called the Josephson energy. And that's manipulated from the outside via some sort of, I think, magnetic induction using microwave pulses. So the important thing to remember about the transmon is that it has this energy landscape, or potential energy landscape. It looks kind of like a parabola, but it's a little bit wider. So the energy levels are not exactly evenly spaced, but there are quantized energy levels, just like just being trapped in the potential well. And usually what people do when they use these in physical computers is they take the lowest two energy states that are possible in the Josephson junction, and they use those as the qubits. And the microwave pulses are used to move them back and forth between those two energy states. And you actually have to take care to make sure they don't go into the higher energy states, because you don't want to use those, because then you're no longer using a qubits. So that is called the computational subspace, the first two levels. And if you want to see, I think it's helpful to see another picture of what they look like. They're about, what's this, maybe a millimeter long. The Josephson junction is about a micron long. Yeah, they're pretty interesting. And there you can see the microwaves go around the outside to induce current. Okay, so you probably looked at that energy landscape and are wondering, well, why aren't we using those higher energy values? We're kind of just throwing those out, kind of like how I set this up, talking about the ternary bits and all that at first. So it is possible to do quantum computing with more than just two state systems. And when you have more than two possible states, it's called a QDIT, where D is for a D-level quantum system. So they all have different names too. Like a 3-level quantum system, you can call it a QTRIT. I think 5-level is QQuint, and so on. And then you can have D levels, however many you could fit into your system. So how do these compare to qubits is the question. So how much information can you store in the QDIT? Well, you can just think about it. Since you have, if you have n qubits, they can be in 2 to the n possible different states. And that's the same as if you have d possible states in your QDIT, then n QDITs could be in d to the n different states. And so they're actually isomorphic to each other, the possible states that they can be in, if your QDIT is a power of 2 different possible states. So for example, a 4-level QDIT that has 4 possible states, that's the same as 2 2-level qubits. They can map to each other because there are the same number of possible states. You cannot directly map, however, a QDIT that's not a power of 2 to qubits. So a QTRIT, for example, there's no exact correlation between the number of states that you can have. You can use 2 qubits, but then there'll be an extra state that you're not using. And another thing to note is that you still need entanglement in order to do a lot of algorithms. So you still need multiple qubits to do some operations. You can't just make an arbitrarily large qubit and do all of your operations in that space and never have to worry about entanglement ever again, unfortunately. So you've seen before how qubits can be written as 2D vectors. So 0 would be the 1, 0 vector, and then 1 would be the 0, 1 vector. And then you can represent all of your quantum computing as linear algebra. It's pretty great. And all of your unitary operations, your qubit gates are unitary operations in SU2. Like, for example, the X gate just flips between the 0 and 1 states. You can easily see how that works. So another example would be for QTRITs. You're just adding an extra state in, and I'm not showing the normalization, but it's a normalized 3D complex vector. And the gates in that space are similarly in SU3. So the vector space is 0 is 1, 0, 0, and then 1 is 0, 1, 0, and 2 is 0, 0, 1. And you can see that forms the basis, and you just have a 3x3 matrix representing your operations. So I put this one up here as an example. I call it XA. And this is an example of a gate which acts on a QTRIT. Does anyone know what it does? Anyone tell me? Exactly, yes. It'll swap whatever the probability of being in the 0 state with the probability of being in the 2 states. And it leaves the first state alone. And in general, you can make a D by D matrix where D is the level of your qubits, and those can be your quantum gates for higher level systems. There's one neat example here of how just one QTRIT, one multi-level piece in the system, can lead to a substantial increase in efficiency. So the Toffoli gates, if you've seen how it's been decomposed into qubits, that's what the Toffoli gate is on the left here. If you want to write that in terms of two qubit gates on qubits, you need at least 5 CNOT gates involved. And it looks really complicated. But if you allow just the target qubit to be a QTRIT instead, so you give it access to the higher energy state, and then you decompose it in terms of QTRIT gates, you only need then 3 2-qubit gates to decompose it, which is a substantial difference from 5, because 2-qubit gates usually take up most of the gate time. So this is about twice as fast. And here you can see the XA gate that I showed before, which swaps the 0 and the 2 positions. If you start with that, you take whatever, if the target qubit is in the 0 state, you put it into the 2 state instead. And then all of these other operations don't have any effect on it, because there's just the 2-qubit gates between the 0 and 1 states with the Hadamard and the CNOT. I'm not changing those. And then at the end, it should still be in the 0 state, so you swap it back. And it has no effect on the 1 state. So it works as you would hope there. And it turns out if you do all of these gates, you get the Toffoli gates. And at the end, there's no chance of the target qubit being in the 2 states. It's just used as an intermediary, which is pretty neat. So it makes you think maybe we should be looking more into using these higher energy states. Another interesting difference, I think, between the qubit gates and QDITs is for controlled gates, since each qubit only has 2 possible values, you can only have 2 possible outcomes when you apply a controlled gate. So it's sort of do a thing if it's 1, or don't do the thing if it's 0. But if you have your controlled qubit allowed to be in many more states than just 2, you can have any number of different unitaries, which are performed depending on what the state of the controlled qubit is. And this can lead to increased efficiency as well. And it just looks so pretty. So before I move on, I want to stop for questions, and then also want us to think about what are some other possible advantages you can think of that QDITs might have over qubits. So ideas or questions? Yeah.
Do common simulating softwares allow you to access these higher energy levels? Like, for example, if I want to IBM quantum experience, would I be able to do this following deconstruction?
And simulations, I think so. I know you actually can use the higher energy states of IBM's devices, and there are tutorials to do that. And actually, I include one later on in this talk. Yeah. Anything else?
And from the hardware perspective, it might be easier to
Yeah.
have to fabricate a small qubit device that can do the same, let's say, like number of operations, whatever, say number of K operations.
Right. That's really important nowadays because we're struggling to build large systems of these things. What if it costs a lot less to build a computer out of fewer qubits than out of a lot of qubits? You could save time or money, or maybe it's not even feasible to have too many qubits.
More of a scalability thing rather than time and money. Like,
Right. That's more important, I think.
33 qubits was like this big. That's giant.
Right. So sometimes when you put a bunch of qubits together, it just doesn't work. And we really need error correction to solve a lot of these problems. But in the meantime, we're looking for creative solutions, and QDITs could be one of them.
Are you gonna notice that?
Was that?
Like why you might be able to compensate like the need for error correction with having qubits?
Well, there's actually, I didn't find a lot of
I don't know.
research on error correction with QDITs, but
My general understanding is whether you have a QDIT or a qubit, you're still gonna require error correction, right?
Yeah.
yeah.
And I mean, there's also, I think we need to distinguish, there's physical qubit or QDIT, but you can always represent, n states in binary or tertiary, or like you could just label them in binary. So you could apply like your theory of error correction to this as well. The implementation might look different.
Right. Like we did see that the space of QDITs states are isomorphic to the state of qubits. So in general, the theory works the same.
Right.
Mhm.
Yeah. I didn't know if there was maybe some leading ideas about why you might
Right.
not require error correction at some point with qubits. That wouldn't be clear to me.
Oh.
You're saying you haven't
I-
found it, right?
No, I wasn't trying to say that. No, but in the meantime, we're looking for creative things. So like if the solution in the meantime, if we can't do error correction, is to do things really fast so that there's no decoherence and we don't have to worry about the errors as much. And this is one way to potentially make algorithms faster. In that sense. Yeah, so I'll move on then. So there are ways that people have made physical systems out of QDITs so far. Here are 2 interesting ones that I found. On the left here, you can have photonic qubits. That's where the energy of your photon is quantized. And rather than just having two different energies, you have many different possible energies of the photons. And you can think of them as different colors, and each color gets its own state. And you can people have built qubits out of those. There's also trapped ions. So people use the energy states of electrons and ions as qubits, which we saw before, but also when there are multiple possible energy states for the electrons and the ion, you can have more than just two possible states. You can have any number of energy levels that can be occupied. You can treat that as a qubit as well. And bigger ions might have more energy levels that can be occupied. So it's important, if you're using trapped ions, you can have a theory of how to do your algorithms based on how many energy levels are available to you in each of your qubits. And more importantly, that I'll dive into more detail on, there are qubits on transmons. This is what I hinted at earlier. All we need to do to turn a transmon into a qubit is allow yourself to access those higher energy states, because the only thing stopping you was putting protocol. You actually have to put protocol in place to prevent the jumping into the higher energy states if you want to treat a transmon as a qubit. But to treat it as a qubit, you can just allow those transitions to happen, but maybe not allow it to transition into, say, the third state or the fourth state to keep it bound. Yeah, but if you want to use qubits like this in an actual algorithm, you also need to come up with a way to do the gates, because our universal set of gates that we usually use is built for qubits. It's not always directly mapping into qubits, sorry. So sometimes you need to make your own customized gates in order to do operations, which is another reason actually why people stick to qubits usually. But there is a way to do that. It's optimal control, which I'll talk about in a second. But first, I do want to point out this tutorial on IBM. You can access the higher energy states on IBM's devices. They will allow you, if you have access to pulse level control. I think you still need a research account for that. It might be open to the public now. They keep changing it. But you can at least read the tutorial. It's very informative on how this is done. So if you've seen a graph like this before on the left, this is the discrimination of how you decide whether a qubit is in the 0 or 1 state usually on a quantum computer. You apply a pulse, and then you measure in these two values. There's the in phase, it's the I, and the quadrature phase values. I don't fully understand what those mean, but they're what you get when you measure. And then you do some classical cluster analysis, so machine learning usually, to create a way to discriminate, given a single point, which measurement it corresponds to. So 0, 1, or 2 in this case, where normally it would just be the blue and the red dots, but they've added in the green dots. And you'll see there's actually some error associated with the discriminator, the clusters being too close in this case. But this depends on the device, and actually, in order to make a quantum computer, you need to do this for every single device and every single qubit on the device in order to get accurate measurements. But in order to do these measurements, you also need a way to put your qubits or qudits into the proper state, so you know where to put it, whether to make it blue or red when you put it on the graph, or green. And the way to do that is with this Rabi experiments. So it uses the fact that if you subject the qubit to a microwave pulse at a specific frequency, which also depends on the device. It will oscillate between two states. So in either 0 or 1 or 1 and 2, for example. So if you do it at specifically the resonant frequency, it will be in one state. The amount of time it takes to get between the states will be the amount of time it takes for one period or half period of the oscillation to occur. So you do these experiments applying the pulse at the resonant frequency for a different amount of times, and you get this plot that looks like a sine wave. You can measure the distance between the bottom peak and the top of the peak, and that gives you the pulse which you can apply to the system when it's in the 0 state to turn it into the 1 state with very high confidence. And that's how you're able to discriminate them. And in the IBM tutorial, they also talk about how to do it between the 1 and the 2 state to get all 3 to discriminate. You could do it directly from the 0 to the 2 state as well, but they say that their pulses are not strong enough to do that. So that has an effect on it as well. Yeah.
So when you show the essentially the histogram distributions of IQ, so this is done in QuIC pulse or something?
Yes. So you need to use QuIC pulse in order to apply the microwave pulse, which you get from the Rabi experiments.
So do they mention anything? You said something about this, about the fidelity between the 1 and 2 states here, because like the distributions are quite close together.
Right.
Do they mention how you extract like quantitative?
They do that. It's just part of the statistical analysis of this plot on the left. Yes, you can do that.
Like the histogram.
Right, right. I think there were histograms and everything, but you should look at this tutorial. It's very interesting. Right, so next I'm going to talk about optimal control. So we've seen that you can use pulses to do specific transitions between states, but we want to do, say you want to do more general quantum gates, so more general operations going from some state to some other state. In that case, we use a mathematical technique called optimal control, which is really just a fancy way of saying optimization, where the control is the signal, the microwave pulse, and the optimization is finding the correct values of the pulse to produce the desired output, which is the pulse which produces the transition that you're looking for. So I like to think of it in terms of this drawing over here. So the state of your qubit can be thought of as a vector on the Bloch sphere. And when you apply the microwave pulse to the superconducting qubit, that vector sort of wiggles and moves around the Bloch sphere. And eventually it stops somewhere else at the end of the pulse. So what you can do is you can pick a certain starting position for the vector, apply the pulse and see where the vector ends up. And then you tune the pulse in such a way it becomes an optimization problem so that your final vector points where you want it to. And that is just the optimization process that produces the optimal control pulse. Am I explaining this clearly enough? Are there any questions here? If not, I'll keep going. So here's an example that will help you see on a QDIT actually in this paper that I found. This is showing how the pulse over time acts on each specific basis state of the QDIT. So you need to start in different positions. So you can start with the vector. It's no longer on a Bloch sphere, but you can start with a vector in the 0 state or the 1 state or now the 2 state. And you see how the pulse acts on each of those over time. And what you really care about is at the end of the pulse where the vector ends up. And in the middle, you kind of see how the pulse interacts with the state in the middle before it gets finished. You have a question?
Yeah, the last one, say it's 3.
Yeah.
The blue one just disappear, and then yellow and green one say.
I think the blue one is down underneath the yellow and the green, and you can't see it. But the point with this is this pulse is explicitly not touching the higher energy state. It's only looking at the 0, 1, and 2 states, and it's keeping the 3 states the same throughout the entire pulse. And you can actually enforce that in the optimization process if you want. Otherwise, you can just have it start and end at the same position, kind of like the psi equals 1 part, which starts at 1 and then does a little thing and then ends at 1. Yeah, so can anyone tell me what this pulse, what gate this pulse corresponds to? So I'll give you a hint. You just look at the start and the end of each vector, of each graph. So, yeah, no, wait. Not quite. No. This is a three states. This is a QuIC gate.
Yes, we can have like a 3-qubit CNOT in some way. I'm not sure if that works.
Right, you could.
But interestingly, I mean, you could write this actually as a CNOT gate if you mapped it to 2 bits, 2 qubits. You could map this to a CNOT, but I think.
Oh, maybe.
Because if you include the 3 state, then there's technically 4 states. You're leaving 2 of them alone, and you're swapping the other 2. Okay. But
Okay.
if you ignore the 3 state, yeah, then it's the gate
But-
that we discussed earlier, right?
That's what I was going for. Yeah.
0 and the 2.
Leaves the 1 state alone. The 0 goes from 1 to 0, and the 2 state goes from 0 to 1, or 2 to 0. I probably said that wrong. But it's basically swaps the occupation probabilities of the 0 and the 2 states. So this is the pulse application of the XA gate that I showed before. Also, I mentioned that we only wanted to look at how this pulse acts on each basis state, and I wrote why. Would anybody like to take a guess why we only look at these specific states and we don't have to look at any arbitrary states as well to see how the pulse works?
You want to write down the gate as a matrix. You only need to know how it operates on the basis states, and then from there you rotate the matrix any other basis.
Right, that is true. So you can essentially write any state of the quantum system as a linear combination of these basis states. But also there's the fact that this operation that corresponds to the pulse is unitary, and it acts linearly on each of the states. So it's sufficient to see how the unitary operation acts on each individual state to understand how it will act on any arbitrary state in the system.
Hey, Joey,
Yeah.
Manquilla from the chat asks, is there a plot of how the pulses look like? Is there a plot of it?
Not for this particular one, but for another one that is coming up. Yeah, and I think it's on the next slide. No, it's on the slide after this one. We'll see what the pulses look like on the system. But I'm going to, because I didn't do that experiment, that was one that I found online. This is one that I'm more familiar with. This is the simulation of nuclear physics that was promised, doing optimal control on to do a quantum simulation of a system of 2 nuclei, so 2 neutrons. So the Hamiltonians of the device of any superconducting circuit, in fact, is given by this HD here, and the Hamiltonian which influences it based on the microwave pulses are this HC here, and there are actually two components to that, which are going to be controlled. There's the epsilon I and epsilon Q parts. So there are actually two different pulses you need. One of them is the in-phase pulse, and the other is the imaginary or quadrature phase pulse. And you need both of them, in fact, to fully describe the system, because it's there's complex numbers involved. But basically, these are all of the this is all the information you need to understand how a device will respond to a microwave pulse without actually having to run a pulse on an actual device. So this allows you to use classical simulation. You can simulate what the actual circuit will do if you subject it to a certain pulse. And this, of course, speeds up the optimization substantially, because you don't have to keep running QuiC jobs every time you want to check the output of your pulse. You can instead just do it in classical simulation. And here's, so I wanted to look at this more close-up version of the transmon potential energy landscape. So there's 4 states which are allowed in this example, the 0, 1, 2, and 3. And those are directly mapped onto, for the desired system of the 2-neutron system. And we're looking at the interaction of the spin-spin of the 2 neutrons. So there are 4 states that are relevant, where they're both down, both up, and then 1 each way. And so this is the pulse that is outputted after the classical simulation, which is determined to perform the unitary operation that corresponds to the potential, the time evolution of the 2-neutron system that we're observing, which we are simulating in the quantum computer through this gate. So this is what they look like. There's sort of, you can see they're between -15 and 15 megahertz in that energy range. And the amount of time is about 100 nanoseconds. And you can tune either of those parameters. You can have higher energy pulses or longer pulses, and just do the optimization the same way, and you'll get a pulse that produces the state that is desired. The main difference you can, so to visualize what's happening with this pulse, is if you remember the block sphere, I described the action of the pulse on the block sphere on the system as the vector rotating around the block sphere. Well, the shorter your pulse is, the more wild that rotation is. And so, or the faster it has to be. So depending on how long your pulse is, or what your parameters are, or whatever the optimization comes up with, you'll have any number of different possible paths to get between the initial state and the target state. And that's something you need to watch out for, because if you make the pulses have too much energy, then your vector could just be spinning all over the block sphere, and then you'll get a lot more error in the final state. And here's the results that was used from this simulation. So that pulse, which performed the unitary gate, which was the time evolution of the 2-neutron system in the with the spin interaction potential. That pulse actually can be recalculated for any value of delta t. So you can actually see, so that the delta t in the e to the minus I over h v delta t. So you can actually see where the system will end up based on how long the potential is applied to the system. So you can get a picture over time, and then you can do Fourier transform to find the different possible values of energy, the energy eigenstates of that of the Hamiltonian of the system. And this was also done via simulation with also factoring in decoherence. But you can see it still did a good job of predicting, in this example, what the energy spectrum looks like. So this is a promising result for 4-level QDIT, at least, of how this can be applied to quantum simulation. And this is all I want to talk about. So are there any questions? Yeah.
I'm a little bit confused by the pulses.
The pulses, yeah.
Yeah, what state are you taking? Because those are 2 different pulses. What state are you
Mhm.
taking your system to in either of those, do you know?
So there are 2 pulses. Yeah, maybe I'll go over to this picture again. You need 2 pulses because there are 2 microwave cavities. You see the green wire and the red wire.
Yeah.
And it's something in the way that transmons or the
Like,
superconducting
how big is
qubits are built.
Is in the cavity the meander and the CPW right there? No?
Which one? Wait.
The wavy,
Wavy guy?
empty space.
That's not where the lines are pointing on this picture, so I didn't think so.
The thing there, it's like the wider squiggle, black squiggle is the passive.
Oh,
And
that's the interdigitated
Yeah,
capacitor,
and I
right,
think
I see.
green I think is the cavity.
The
And
green,
then I
yeah,
think orange is like a feed line.
right.
So is this mislabeled or what? Am I
No,
misunderstanding?
No, it's just, it's not, maybe it's not misleading.
Oh,
I just was confused. Okay, that makes sense.
Oh.
But I understand the setup. I just
Okay.
didn't like the
so the pulses.
pulse, like the, yeah. it's
Yeah.
not- Pulse sequences, I guess, in QDIT systems is not straightforward.
It's just voltage over time.
Yeah, I know what a pulse
So
is.
yeah.
Sorry.
Okay, maybe I'm confused what you're asking.
So I think the 2 plots are the amplitudes of each quadrant. So
Okay.
it's a single pulse, but one of them is like this, the amplitude of sine wave, the other one the amplitude of cosine. So
Okay.
they're doing different rotations about like the x and y axis.
But are they for just one single QDIT operation or QTRIT operation? Okay. And
Correct.
so now you need 2.
Yeah, because like in drag, you need to drive both quadratures simultaneously.
Okay.
Whereas like
Yeah,
you know, a regular X gate or whatever is just a sine wave or cosine.
Right.
Sorry, I feel like I don't understand the quadrature. What is this?
So you have a voltage signal applied to this, and it's a wave at the frequency of the Q frequency, 5 gigahertz or whatever. But then what you do is you say, if it's a sine wave, that counts as a rotation above the x-axis. If it's a cosine wave, that counts as a rotation above the y-axis.
Oh,
So they're out of phase, so therefore they're x, y.
Oh,
And so the y-axis here, one is EQ, so that's, say, rotation above the x-axis. And the E9 will be a rotation of the y-axis. So you're sort of simultaneously rotating about some superposition of x and y with different strengths
okay.
in time.
I did not put together the subscript as I do, for whatever reason, my brain did
So
not
you're
think
like,
that.
yeah, rather than just rotating about x or y here, it's about something.
Okay, so if you overlay these plots, would they look like sine cosine? Would they be?
So this is just the amplitude of the sine or the cosine.
Oh,
So
okay.
all the frequency stuff is like in the argument.
Okay,
This is just like the strength of the pulse, about a strength.
Hmm.
gotcha, okay. And then Nicola, let's see, I think he was asking about the pulse sequence. So this is the pulse sequence you're referring to. So Holland et al., do you have is there a year for that? Because I think Nicola wants a reference, he wants to look this up later. Holland et al.
Yes, that was also Sophia Quaglione was also on that paper
Okay.
I'm working with. It was called Optimal Control for Nuclear something. Yeah.
Cool, thank you.
Okay, I think you'll find it then. Yeah.
So I understand you can use like the transmon to represent many levels.
Mhm.
But I think I'm a little confused. So the transmon's a single, like it's one qubit, right?
Mhm.
It's like a single. And you're using it to simulate 2 neutrons, which are 2 things.
Right.
So I understand, 4 levels is 4 levels, so that works out. But like if I take the transmon state to be a superposition of 0 and 3, according to the picture you have here, that's just like an arbitrary superposition state, but it corresponds to an entangled state in the neutron system.
Right. And I did say entanglement is important.
So
yeah.
So like it seems to me like I can't have a transmon entangled with itself.
I have a
In the
very
circuit
strong
you
opinion.
showed,
It seems,
Oh,
it just
I'll let
seems
Jacob
like-
answer then.
No, sorry, I've gotten into heated debates about this, and so I've thought about this for way too long.
Okay, so this isn't something I never thought of before today. So
Yeah.
I guess my question is like, is there an inconsistency?
No,
Like,
sorry,
there's not.
there's not, no.
So,
Okay.
Contrary to what some people have argued
But-
said.
it's not obvious.
You're representing entanglement. So the system that Joey's describing that they did here is not itself entangled. It's not two systems that exhibit correlation to each other that are beyond classical. But it is representing a system, just like in this, like a classical computer can represent an entangled system. This quantum system is representing an entangled system. But there's no, you're not, if I wanted to query one, if I wanted to do a measurement on one of the two neutrons, that's going to correspond to some weird operation in the system, right? It's going to correspond to it. It's not going to be querying, one piece.
So does this mean you can represent entanglement, but you can't like use the power of entanglement?
Yeah, well,
Right, because you can't do like quantum teleportation with
Right,
this,
'cause
because you can only measure the whole system at once.
Yeah.
Basically.
So you can't do like.
but you could represent the process efficiently.
Mhm.
Assuming access to.
You couldn't write down a Hamiltonian which corresponds to the measurement of a single neutron and enact it on this system. Is that right?
You could, of course, you could write it that Hamiltonian that would do that. So, let's see,
Oh,
so
right, because this is not a 2 level.
because maybe you're interested in, let's do it in binary. So 0 is 0, 0, 1 is 0, 1, right? So if you have the Bell state, so that's 0 plus 3, you want to measure, what might you want to measure? Maybe you want to measure the parity. Maybe you want to measure, is it in the 0, 3 subspace or the 1, 2 subspace? And then you would measure which two Bell states, which two classes of Bell states you have, right? So you can map it. You map the measurements in a different way. Yeah.
Mhm.
So it's not entangled, but it has the same power. I think the thing with entanglement is in practice you're going to have to entangle many particles because in practice you don't have access to a billion quantum states that are easily accessible in one system, if you will, like one.
Yeah. Well, I guess the important thing with entanglement is it is necessary if you want to build a universal set of quantum gates in order to have for multiple qubits. You need at least one gate which is 2 qubits and involves entanglement in some way.
And unless you had this very strange, experimentally, I'm not saying this is viable, but if you had access to all the levels of hydrogen, you could use that as a computer. Just of course, it's not viable. But if one were able to do those operations easily translate between those, I think,
So you're not losing anything here because you're focused on like a simulation versus the universal set of gates.
Right.
So you're not losing. Okay. Interesting.
There are some algorithms that do not directly map over in that sense, or maybe, well, some experiments rather, because of what you lose in the ability to measure the individual states.
Cool. Thanks.
any other questions?
Yeah, go back to like the clustering page.
Yeah.
So it looks to me like these, the 1 and 2 state aren't really like viable states because there's quite a bit of overlap between the clusters. Is that like
Mhm.
something you can control to like, maybe you could do change something in the experimental setup to I'm gonna try and use until I have a better IMQ that give me the correct qubit?
Yeah. Well, I mean, this whole thing does depend on the specific device. So I don't know how different they all are or what needs to be changed It might have something to do with, yeah.
They're usually their own budget, it seems pretty distinguishable.
yeah, if you get that, then you would have much better fidelity in determining which state you're in. It's okay.
So yeah, you need to run the survey.
So this is typical. I guess there's maybe if you increase the distance and the energy levels, but then you have trouble in getting and transitioning between them consistently, I think.
So sorry,
So-
the question was actually about the Wu paper.
Oh.
For the reference. My bad. Yeah.
Wu et al.
Yes.
Yes, this was,
Wu.
oh, I picked not a good name to cite there,
Maybe,
sorry.
maybe you can get that to Mancoba by email or something. I can help set that up.
Yeah, this paper was just QDIT, pulse gates on a QDIT or something along those lines, optimal control. I don't know if it even had the word optimal control in it.
Do you think they have the
I think I searched optimal control on QDIT and it popped up that way.
I don't know.
So,
really feel like-
yeah.
So I don't necessarily know if this is true, I've heard it, that like the reason that these higher level, like classical computer machines didn't work out, like these 3-state machines or whatever,
Uh-huh.
is that you kind of, whatever you gain from that, you kind of lose in that the gate operations take longer to perform, or it takes like longer to distinguish which state it's in.
I can see
do you
that
know
to be
if,
true.
Like the pulse stations that you need to implement similar gates is affected between qubits and qubits?
Well, I mean, just looking at the amount of time the pulse takes, that they're usually around 100 nanoseconds like these, which I think is about the same for 2 qubit gates. I mean, the problem with the optimal control is if your system is too big, then this optimization might be really hard to do. So that would definitely take longer. But yeah, I don't know for QTrits, I don't think there's any difference in the ability to apply the 2 qubit gates or 1 qubit gates. It's about the same.
All right, let's give Troy a round of applause. Yeah, so again, we're off next week, but we'll very likely pick back up 2 weeks from now. So thanks for coming.
I want to find this.